Hello everyone. In this lesson we're going to simplify and eliminate any radical expressions in the denominator by rationalizing the denominator. So before we get to that, let's go ahead and work on the do now. Anytime you have an odd exponent for a variable, that means it is a non-perfect square. And the way you make it a perfect square times a non-perfect square is to minus 1 from that exponent, that odd exponent. So the first thing that I see is the square root of x to the fifth. I am going to create a perfect square radical and a non-perfect square radical. Since this is a non-perfect square, I'm going to minus 1 from it. And it'll become x to the fourth. X to the fourth times x will be x to the fifth. So the square root of x to the fourth, which is a perfect square, is x squared, because x squared times x squared equals x to the fourth, and the square root of x comes down right next to it. For this one, again, we have 8, which is a perfect square. Y to the 9th is a non-perfect square, and z to the 14th is a perfect square. So what we're going to do is we're going to create a perfect square radical and a non-perfect square radical. X to the 8th is a perfect square, so I'm going to put that in the perfect square radical. Y to the 9th is not a perfect square, so I'm going to subtract 1 and put to the 8th power and put to the y to the first power in the second radical. And then z to the 14th, and this is z to the 14th power, is a perfect square. So I'm going to put that into the perfect square radical. So the only thing I have in that non-perfect square radical is just y. So square root of y to the 8th, x to the 8th is x to the 4th. The square of y to the 8th is y to the 4th. And the square root of z to the 14th is z to the 7th. And then square root of y comes down next to it because it's a non-perfect square. For this one, again, we're going to go and put a perfect square radical and a non-perfect square radical. 50 is a non-perfect square, so we're going to create a perfect square. We're going to have a perfect square that goes into it. The largest perfect square is 25, and 25 times 2 is the non-perfect square. So x to the third is a non-perfect square, so we're going to put that to the second power times x. X squared times x is x to the third. And then y to the 18th is a perfect square, so we're just going to put y to the 18th right there. So all of these terms are in the perfect square radical. So the square root of 25 is 5. The square root of x squared is x. And the square root of y to the 18th is y to the 9th. And then you would get the square root of 2x. And that is it. Okay. So in today's lesson, we'll be rationalizing the denominator. In order to understand this topic, we must understand the properties below. So we're going to rationalize the denominator. Remember, that is the bottom number of a fraction. So the multiplication property of square roots says that if you say the square root of 54, we could split it up into a perfect square and a non-perfect square. So the perfect square would be here, 9, and the non-perfect square would be 6. The square root of 9 is 3. The square root of 6 would be your final answer. So I'm just going to go, before I go on to the other property, I'm just going to simplify the square root of 50. Square root of 50, again, is a perfect square times a non-perfect square. So that means 25 is the largest perfect square that goes into 50 times 2. And we can have 5 radical 2 because the square root of 25 is 5 and square root of 2 is a non-perfect square. For this one, we have -3 times the square root of 300. The largest perfect square that goes into 300 is 100. So 100 times the square root of 3. So we have negative 3 times 10 because the square root of 100 is 10. And then the square root of 3 comes down right after it. So this is negative 30 square root of 3. And let me just put that on the side here. I don't want to squeeze it in. That becomes negative 30 square root of 3. Negative 3 times 10. And then the last one on this side, 13 times 52. The rule is underneath the radical. If there's a number underneath the radical times another number underneath the radical, you can multiply those two numbers. So I'm just going to do 13 times 52 to see what that equals. That is 676. So square root of 676. So just to make sure, I don't want to, I don't know if 676 is a perfect square. So I am just going to go and put 676 into my calculator. And it is a perfect square. So you always check to see if it is a perfect square. I didn't know right away. I didn't know that 26 times 26 equals that. So you didn't have to break that up. It is just 26. It's a perfect square. And that is it. So let's go back up and talk about the division property of square roots. So the division property of square roots says that if you have this kind of example right here, you could split that numerator and denominator up. So it could become the square root of 16 over the square root of 25. And the square root of 16 is a perfect square. It's 4. Square root of 25 is a perfect square. It's 5. So let's see if we can kind of work and simplify these right here. First off, before I split it up, I'm going to do 90 divided by 5. And 90 divided by 5 is 18. So I'm not really using the property, but I'm just making it easier for myself. So I'm just going to go the square root. Now, dividing this 90 and 5 doesn't release the numbers from the square root, from the radical. So this is 18. And now I could split it up nice and easy because there is a perfect square that goes into 18, and it's 9. So everybody should know 9 times 2 is 18. And 3 is square root of 9, and square root of 2 comes down next to it. All right, so 48 and 75. Let's see. Let's talk about making the square root of 48. We're going to move that on top, and then the square root of 75 on the bottom. So take a look at what I'm going to do. I know that the square root of 48 is a non-perfect square. So I need to put a perfect square house and a non-perfect square house. When I say house, radical. So square root of 75, the same thing. Perfect square times a non-perfect square. So 48. Let's look at 48, and I'm going to go 48. Let's see, 36 doesn't go in 6 times 6. 5 times 5, 25 doesn't go in. Let's see if 16 goes in. It does. 16 times 3. So 16 is the perfect square that goes into 48, and it's times 3. 75, I already know. They use 75. They use 50. They use 125. They use 150. It is the same perfect square that goes into all of those numbers. It's 25. So 25 times 3 works there. So now take a look at the top now, the numerator. Square root of 16 is 4. Square root of 3 comes down. Square root of 25 is 5. And then square root of 3 comes down right next to it. Now, You see the square root of 3 over the square root of 3? That cancels out, and it equals 4 over 5, and that's your final answer. All right. So we're looking at this right here, and I'm going to just go ahead and do square root of 144 over the square root of 9, and that's a perfect square. So square root of 144 is 12, and the square root of 9 is 3. If you put this whole thing into the calculator, it'll give you 4 as an answer. So D is right here, and we're going to have some work to do here. So I need some room. I need some room. Perfect square and a non-perfect square. And then I'm going to put that over, let's see if I could draw a nice straight line. That's a perfect square house and a non-perfect square house. And then another perfect square radical and a non-perfect square radical. Okay, 75, 25, and 3. X to the 7th, x to the 6th times x. One thing you do have to do is to make sure that you have a lot of room, and I did not do that. So I'm going to put 25 back and 3, because 25 times 3 is 75. X to the 6th is a perfect square, times x equals x to the 7th. Y to the 2nd times y is y to the 3rd, and z to the 10th is a perfect square already. So I'm just going to put that in the perfect square radical. So now 8, the large perfect, or the perfect square that goes into 8 is 4. So I'm going to put 4 times 2, non-perfect square. X to the 3rd is a non-perfect square, so I'm going to minus 1 from that 3 and put the x there, times x squared times x, which is x to the 3rd. Y to the 9th is not a perfect square, so I'm just going to put minus 1 to the exponent. That's y to the 8th. Y to the 8th is a perfect square, times y. And then z to the 4th is a perfect square, so we're going to leave that in the perfect square radical. So I'm going to just take the top part here. I know that everything in the first radical is going to come out of the radical because this is my perfect square radical. So square root of 25 is 5. Square root of x to the 6th is x to the 3rd. Square root of y squared is y. Square root of z to the 10th is z to the 5th. And then square root of 3xy is my non-perfect radical. The square root of 4 is 2. The square root of x squared is x. The square root of y to the 8th is y to the 4th. And the square root of z to the 4th is z to the 2nd. And then square root of 2xy. And the only other thing that you could possibly do here is to cancel out the x and the x. So the final answer would be 5 over 2. I'm going to put this (5 over 2), x to the 3rd, x, y, y to the 4th, z to the 5th, z to the 2nd, and then square root 3y, square root 2y. And that is it. And you could cancel out the y's as well. And that would be square root of 3 and the square root of 2. And that's it. All right, and that's your final answer. All right. Okay, rationalizing the denominator. So this is the whole part of like, hey, the lesson is rationalizing the denominator. Sometimes the denominator of a fraction is a radical. With a radicand, that is not a perfect square. You must multiply the fraction by another fraction that is equivalent to 1. This will eliminate the radical form from the denominator, right? So simplify by rationalizing the denominator. What we do here is that we're taking square root of 27 times over the square root of 3, and we have to rationalize the denominator by multiplying by a fraction that is equal to 1. So it's easy to make a fraction equal to 1. You just use the denominator here, the square root of 3, and multiply square root of 3 over the square root of 3. So it's like you're multiplying by 1. It is multiplying by 1. So this is now square root of 27 times the square root of 3. And square root of 27 times square root of 3, 27 times 3 is 81. So the square root of 81 is 9. So I'm going to put the square root of 81. That's perfect square. And then square root of 3 times the square root of 3 is the square root of 9. Right? So square root of 81 is 9 over 3. And the whole answer becomes 3. And that's it. All right, so that's simplified. Rationalizing the denominator. So same thing. We have to get rid of the denominator that is a radical 3. So you're going to multiply by radical 3 over radical 3, which is 1. So 6 radical 3 over square root of 3 times the square root of 3 is 3. It's the square root of 9. And square root of 9 is 3. So 6 divided by 3, one last step, is 2 radical 3. 6 divided by 3, numbers outside the radical can be divided. And that is simplest radical form. So we're going to try these all, and we seem to be focusing on radical 3 being multiplied. So that's the first 3 problems. So here we are, and we're going to say this is equal to 5 radical 3, and this is over 3, because square root of 3 times the square root of 3 equals the square root of 9. Square root of 9 is 3. So anytime that you have the square root of 3 squared, that equals 3. Equals the number underneath, because the square cancels out the square root, and it's just 3. So that's exactly what happens when you're rationalizing the denominator. So we're going to take the square root of 6 over the square root of 6. We're going to rationalize that denominator. The top is, the numerator is square root of 18 over 6. Because the square root of 6 times the square root of 6 is the square root of 36. And the square root of 36 is a perfect square, which is 6. So square root of 18, now we're going to take that numerator, we're going to break it up into a perfect square and a non-perfect square, which is 9 over 2. I'm sorry, square root of 9 times the square root of 2 over 6. Move this over, move this over, because we're not done. Square root of 9 is 3, square root of 2 comes down next to it, and then it's over 6. So 3 over 6 is 1/2, you could put it down as 1/2 1/2 radical 2. And you don't need the 1, so I'm just going to get rid of it. So it's radical 2 over radical 2 over 2. And that's your answer. To rationalize the denominator, you would have to multiply by square root of 15 over the square root of 15. And that will equal, let's see, 5 times 15 would equal 75. So the square root of 75 over 15. You know it's 15 because square root of 15 times the square root of 15 is 15. All right, they're inverses of each other. So now I'm going to go down here, and 75 needs some work because it's a non-perfect square. You know a perfect square goes directly into that. Square root of 75 has a perfect square of 25. That goes into it, 25 times 3. So we're going to have 5 radical 3 over 15. And we're going to reduce that 5 over 15 to 1, right? 1 over 3. So we're not going to put the 1. We're just going to put the square root of 3 over 3. And that's your final answer. For this one, you're going to multiply by square root of 5 over the square root of 5. This is 5 square root of 5 over 5. 5 over 5 is 1. 5 over 5 is 1. So that means they cancel out, and it's the square root of 5. Kind of cancels each other out. But it's equal to 1. For number 5, we're going to go and put down the square root of 3 because we want to rationalize the denominator. So we're not going to multiply by the 2 that's next to the 3, just the radical 3. So for radical 3, we're just going to put that as square root of 12 over 2 times 3. And we're going to put that down here. Square root of 12 can be written as a perfect square and a non-perfect square. That's all over 6, 2 times 3. The perfect square that goes into 12 is 4, radical 3. And then we're going to put an arrow, and this is 2 radical 3 over 6. And then finally, we're going to reduce that to radical 3. Right? 2 goes into 2 once. 2 goes into 6 3 times. And that's your final answer. We're going to square root 3 over 3, and we're going to multiply that by, we're going to rationalize the denominator. So that is the square root of 6 over 3. And that's your final answer because there is no perfect square that goes into 6. Right. And that is it. More practice here, simplified by rationalizing the denominator. And we're going to do that right here. Just as soon as I pick a color like that makes a difference. Square root of 6 over the square root of 6. Rationalizing the denominator, you're multiplying by a version of 1. So this is square root of 12. We're going to put that equal square root of 12 over 6. Square root of 12, we're going to put perfect square and a non-perfect square over 6. And that's 4. The perfect square goes into 12. You should know that. Square root of 4 is 2. Square root of 3. And that is all over 6. So it's 1 over 3 I feel like we just did this one. Square root of 3 over 3. Let's rationalize the denominator again by multiplying by 1, which is the square root of 7 over the square root of 7. And 8 times 7 is the square root of 56. And now all that is over 7. So in 56, we have one perfect square and a non-perfect square over 7. So what's the perfect square that goes directly into 56? Okay, so I'm going to start with 6 times 6, 7 times 7, 49, 6 times 6, 36, no. 5 times 5, 25 doesn't go in. 4 times 4, 16. So I'm going to check 56 divided by 16. It's 3.5, no. 56 divided by 9, which is another perfect square, no. 2 times 2, 56 divided by 4, yes. All right, so 4 is the perfect square times 14. So that equals 2 square root of 14 over 7. Now square root of 14 is, there's no perfect square that goes directly into it. 2 over 7 can't be reduced. We're good. That is the answer. So here we go. We're going to, if this doesn't go popping back up again, rationalize the denominator by multiplying by square root of 3 over the square root of 3. So all of that equals square root of 12 again over 3. And the square root of 12 is 4 times 3 over 3. And you get 2 radical 3 over 3. And you can't reduce it. It's good. Square root of 15 over the square root of 15. I don't know what 21 times 15 is. Don't know. That is 315 over 15. So I'm going to say that square root of 315, all right, is a non-perfect square. And it's a non-perfect square. This is another way you could say, I don't know the actual, the perfect square that goes into 315. So what I'm going to do is I'm just going to press y equals, and I'm going to put 315 divided by x. And when you do this, it'll give you the multiples that equal 315. So you see right here, this is 1 times 315, right there. 2 times this, 3 times that, 4 times this. You're looking at the larger numbers. 5 times 63, no perfect square yet. 45 is not a perfect square. 35 is not a perfect square. 10, 11, 12, 13, 14. There are no perfect squares that go in. So 4 is a perfect square. 9 is a perfect square. So right there. So we're talking about 9 and 35. So that's the perfect square that goes in. So we're just going to go like this, like this. No idea. I probably would start with 10 times 10, which is 100. That doesn't go in. 11 times 11 is 121. 12 times 12 is 144. Those don't go in either. So I've turned to the calculator, and there it is. 9 is a perfect square times 35 equals 315. So 9 times 35 equals 315. Now realize, square root of 35 has no perfect square that goes directly into it. It has no perfect square that goes into it. So that's how you know that you pick the largest perfect square. So square root of 9 is 3. Square root of 35 stays that way. It's all over 15. But it's not finished because 3 goes into 15. So we have square root of 30 over, and 3 goes into 3 once. 3 goes into 15 5 times. And that is a tough one because of this 315. So you really do have to like get your multiples all straight. I mean, you could use the calculator like I just did and divide by x, and then it'll give you the multiples. So that might help, but you still need to know the perfect squares. So this one, I'm going to rationalize the denominator, square root of 6 over the square root of 6. And what that's going to do, 15 times 6, well, I could graph this and clear it out. Should be 90, 15 times 6. It is. So square root of 90. I already know the perfect square that goes into the square root of 90. And then 3. 6 times 6 is 36. So the square root of 6 is 6. So now the square root of 90 is like, I'm just going to look at 90. What times what equals 90? 9 times 10. That's the largest perfect square. And then 10 is, there's no perfect square that goes into 10. So you know that you picked the right numbers. So 6 times 3 is 18. We're going to write 9 is 3. Square root of 10 over 18. And we need to reduce that. 3 goes into 3 once. So we're going to reduce it to 10 over, and then 3 goes into 18. How many times? 6. And that is your final answer. Let's talk about this. We're going to multiply by square root of 7 over root of 7 to rationalize the denominator. We're going to get to a square root of 21, which is a non-perfect square and has no perfect square that goes into it. So square root of 21 is going to stay whatever it is. So this is 6 times 7, because square root of 7 times the square root of 7 equals 7. And then so we have the square root of 21 over 42. And that is your final answer. So here is the exit slip. Pretty quick lesson here. Which one of the following would be an appropriate choice for multiplying the numerator and the denominator of 2 square root of 2 in order to rationalize the denominator? Square root of 2 over the square root of 5. So what I'm going to do is I'm going to put down square root of 2 over the square root of 5. And then what would it be? So rationalizing the denominator, which one of the following would be appropriate choice for multiplying the numerator and the denominator? So it would be square root of 5. That would be the appropriate choice. So D is your answer. And we're going to simplify. So this is square root of 10 over 5, and we're done. Can't do any more with that. Square root of 10 does not have a perfect square that goes directly into it. And you can't divide these two because they're not both in the radical underneath the square root. And that is it for that. All right, so the summary is next, which means that we are finished with the lesson. Just remember, when you rationalize the denominator, you're taking just the square root and multiplying it by over itself, because the reason why you're creating that fraction is to get the square root, the non-perfect square root, from away from the denominator. So that means that you're not going to have a square root in that denominator. When you multiply square root of 5 times the square root of 5, the answer is 5. The square root of 25 times the square root of 25, the answer is 25. The square root of 100 times the square root of 100, the answer is 100. So don't make it more difficult than it is. It's just a version of 1 that you're making, that you're creating, and you're multiplying that fraction. If it is not a version of 1, that means you could not do this, because then you would be changing the original fraction, and you can't change the original fraction. All right. And that's basically it. All right. Thank you for watching, and I will see you next time.